Good day everyone. So in this video we will discuss about programming watchdog timer and how it operates when you are making this, you are initializing the watchdog timer as a part of other program. Usually watchdog timer is basically for protection. So in case if your microcontroller goes into an unending loop due to some bug or something, then this should prevent malfunctioning of your entire setup. So for that reason watchdog timer will be used. So here we'll be just analyzing how it works, watchdog timer works with the help of the Keil simulation software. So let me get into the code. So here as I have mentioned earlier, so these are the initialization part, and before this I have copied the startup.s up to line number 411. Then coming to here, so I have initialized IO0 DIR set clear and pin register, because I am just going to use this port 0 for making the LEDs to blink. So in LED blink program I am going to attach this watchdog timer, and I'll deliberately make some delay in such a way that your watchdog time your watchdog timer overflows and a reset happens. So that is what I am going to do as far as this code is concerned, and that will tell you how to use this watchdog timer as a part of other code. So coming here, from here the main code starts, and I am initializing the IO0 DIR with 3, which means you are activating port 0.0 and 0.1 as output port pins. So 2 port pins I am making it as output port pins, and I am clearing the 2 port pins over here. Then I'm moving a value of 3 into the watchdog timer mode register, WD MOD register. So when you are moving content 3, that means that it is activating 0th bit and 1st bit into the watchdog timer mode register. So let us check what is the content that is available in WD mode register. Here fortunately the value 3 available over here is the same that I am giving in WD mode. So that's the reason I am going for. So fortunately, since 3 is available here, I am moving the same content that is available in R1 register towards your WD mode register. So this let us see the content of WD mode register. So watchdog mode register, you have this 0th bit connected to watchdog enable. Then your 1st bit is watchdog reset. Then watchdog time out flag in the 2nd bit, and in 3rd bit watchdog interrupt flag. So out of this I am activating this watchdog enable and watchdog reset. So here what I am doing is I am enabling this watchdog interrupt enable, and watchdog reset should happen. So these 2 things I am specifying over here in the watchdog mode register. Then I'm having a value 4 in the R2 register, and I am comparing the value. So actually the watchdog mode initialization is happening in this particular line, WD mode with the number 3, right? So in this case I am reading the content from watchdog mode register to analyze whether in the previous case any your watchdog flag has been set or not. So as can be seen from here, you can see that your 2nd bit is allotted for watchdog timeout flag. So in the previous case, if your watchdog reset has happened, this particular flag will get set. So from that flag we can understand that there is a watchdog reset has happened. So in case if watchdog reset has happened, I am jumping to this part of the code wherein I will be making my LED that is your port 0.0 to blink. So in case if that is not happening, then I am getting into this loop wherein I am using this IO0 clear and IO0 set. You can see your port 0.1 and 0.2 will be 0.0 and 0.1 will be activated. So actually here it is both are clear, that is 0.0 and 0.1 is cleared. Here in this case your only your 0.1 is made high, and then after a delay that is cleared. So this is like when normal operation is happening, right? So when watchdog interrupt or watchdog reset has happened, then it will come into this part of the code and it will make your LED that is your 0.0 to blue. So here you can see that is 0.1 because you are moving 2 into the IO set and IO clear. So here in this case it is 1. So we can understand from the LED that is blinking whether your watchdog reset has happened or not, right? So so once this part is completed, then I am just coming into the code where I am doing this watchdog feed. So that is like I am moving a content AA and 55 into the watchdog feed. So what does that happen? Why we need to do that watchdog feed? Yeah, before getting into the watchdog feed, we need to understand what is the function of this WDTC, your watchdog timer counter. So we'll have to design this and then get into this watchdog feed. So let us see what is a watchdog timer constant. So not timer counter, it's timer constant register. It's a 32-bit register. Its minimum value should be FF. If you are writing anything lesser than FF, it will be by default it will be keeping it as FF. So that you should understand as far as this WDTC is concerned. So I'll show you your WDTC. Here you can see that WDTC register determines the timeout value. Every time a feed sequence occurs, DTC content is reloaded into the watchdog timer. So it's 32-bit register with 8 LSB set to 1 on reset. Writing values below FF will cause FF to be loaded to the WDTC. So minimum timeout interval is given by TP clock into 256 into 54. So this 256 is basically the hexadecimal value of FF. Decimal value of decimal equivalent of hexadecimal value FF. So assuming that the minimum value we are going to feed in your WDTC FF, your timeout interval is given by TP clock into 256 into 4, right? So this is the formula. So as here also I have given WDTC is loaded with FF as 256 is the decimal equivalent of FF in hexadecimal. So crystal oscillator is having a frequency of 12 megahertz. So your peripheral clock frequency is 12 megahertz divided by 4. So these things we have seen in the previous video also. The slashing factor you can go for making it to 1 also, but I am not going to change that one. I am leaving it as such. So your peripheral clock will have 3 megahertz. So if 3 megahertz is your peripheral clock, then your TP clock is given by 1 divided by 3 into 10 power 6. 3 megahertz means 3 into 10 power 6. So that is equivalent to 0.3333 microseconds. So your timeout interval is given by 0.3333 into 10 power minus 6 into 256 into 4, so 0.34133 millisecond. So your feed has to happen, that is your watchdog timer has to be done with the feeding sequence before 34133 millisecond. So that is what we have to understand. We can design this particular timeout interval based on our code. So what is the requirement? So what is the minimum time that can be allowed for your microcontroller to be out of the sequence? So as in this case of the code, it has to come to this part and do this job of feeding. So if AA and 55 is not being done, what happens is your WDTC will be running and it will try to go to 0. When it goes to 0, timeout flag will happen. Timeout flag, when it happens, it will prompt a reset. So to avoid that, within 0.34133 millisecond, your watchdog feed has to happen. So coming to the code again. So here that is what I have given. So here one part I have made the delay in such a way that you can see that there will be repetition of this part of the codes. That is, your feed will happen and then IO set and IO clear with delay will happen, and then feed will happen and clear will happen. These things you can make it as many number of times as you can. And here the delay subroutine I have created with a minimum value. So in case if your delay is happening in such a way that your program could come and do this feed, these two feeds, then your reset will not be activated. But when this value is lesser, your reset, the feed, if it doesn't happen, a reset will happen. Watchdog, not watchdog, the complete microcontroller reset will happen. So let me check with the simulation. So here you can see that IOZ 0 DAR loaded with 3, IO0 clear is loaded, and then I am reading the content of a watchdog mode register. Obviously first time when you are getting into this one, so it will WT timeout flag will not get set, so it will come out of this loop and it will try to make the value of WDTC as FF, and mode I am making it as you can see watchdog enable and watchdog reset has happened. Then further I am getting into it. So I am getting into the delay subroutine now. So you can see the way in which the values are being decremented in this R3 register and your WD TV. So this is a watchdog timer constant and this is watchdog timer value. So this value will be decrementing. So the pace in which this one decrements will be lesser than the pace in which your R3 value is decrementing. So before a reset could happen, this sometimes may go for doing the feed. So let us check that one. So I am just doing this process fast forwarding. So set has happened, now it is getting into clear. So again feed hasn't happened, so let us check again. Again it is coming into this delay subroutine. I am decrementing the value, you can see over here. can see that this WDTV has a significant value, while R3 is coming almost to 0, closing almost to 0, where you can see that it is coming jumping back to here, and WD feed, when you are doing this one, so you can see that the WDTV will get reset to AFF. So when you are doing this, you are making your watchdog not to come and do the reset of the microcontroller. So that is what is being done over here. So this same thing can be repeated for the further on and off process of the individual IO set and IO clear. So here also you can see that now feed is happening. So once feed is happening, this value is getting reset to AFF, and it goes on again like this. So in all these cases I am using the same delay, so no way your reset will happen. So for prompting a reset, let me change this value to 1FF. So now we are getting into this delay subroutine. So 1FF, even if I am doing just a value 1, it means like adding 100 towards it in hexadecimal towards the particular register. So it will have a consistent increase in delay value. So the set is over. Now again after the clear, the delay subroutine is going on. You can see that this value is decrementing, while your R3 value is like having a consistent value. So in this case you may expect a watchdog timer reset. Now your WDTV has gone to 0. This is going to generate it. Now your interrupt has got generated, so your program counter has gone to the starting of the code. So you can see, and WDT off, that is time out flag, this particular bit has got set. So when this is got set, it gets into this particular part of the code where your port 0.1 will be turning on and turning off to represent that there was a watchdog reset. So this is the case for your so in this case, since it is getting into that particular part of the code where your watchdog feed hasn't happened, you can see that this value is not getting updated. So which means that your watchdog timer is not active now. It is just giving out an impression that your watchdog interrupt has happened. That again you can see using your port 0. Okay. Now this on and off is happening as in the case of your port 0.1. So by default your port 0.0 will be blinking. When watchdog reset has happened, your port 0.1 will be on and off for a particular time, and then your normal operation it will get into. So now it has gone into the normal operation, and again your watchdog timer value it is getting decremented again. So let us once check with the complete run also. That will give you an idea regarding how this operates. Now I am just you can see that here this on and off is happening, and again this reset is happening, since I am having a value of 1 FF in the case of your subroutine. So let me bring the value just to 0 FF. So in this case there was no watchdog timer reset. So let us check that one. So you can see here only this one is blinking, that is 0.0 is blinking. 0.1 is not blinking at all, which tells us the fact that your watchdog reset is not happening at all, right? So when this is as a part of any other code, we'll have to design the value of your WDTC in such a way that whatever the time delay that you can give between any two events that is happening, so that if for that particular amount of time if a feed doesn't happen, then your watchdog reset should not happen. So the designing of your program should be in such a way that the value that you give in this WDTC should be ample enough so that unwanted reset doesn't happen. So whenever you are using a watchdog timer, it should be in such a way that it gives a ample time for any particular event that is happening or any particular delay that is happening. So I have created both the cases, like when it doesn't when your watchdog reset doesn't happen, and when your watchdog reset does happen. So the watchdog timer I have deliberately made your program in such a way that watchdog reset will happen, to show you that this is the process that will take place when watchdog timer overflow is happening. But in real case, you should be choosing a value in this WDTC in such a way that that is not a regular process. Your watchdog timer reset is not a regular process. It happens only under exceptional cases where your microcontroller gets into some unending loop, or it's getting into some hang-on situation. So at that time we just want your microcontroller to get automatically reset. So for that case we'll be using this watchdog timer. So this is the explanation for watchdog timer, and there is a watchdog timer with interrupt also. So let us get into watchdog timer with interrupt. Okay, so now I have I'm showing this watchdog timer interrupt program. So I am using the same code, only thing that I have added with this one is the watchdog interrupt. So here I'll not reset the microcontroller. I mean, I have made the program in such a way that when watchdog timer overflow happens, it will not reset the microcontroller, but it will get into the interrupt service routine, and it will blink an LED to represent that there is a watchdog overflow has happened. So this also can be used in certain case of the program where you can understand that there is particular delay time that has been crossed for a particular function that has been used. So for that analysis you can use this one, and you can use this one to understand your working nature of the code of the program also. So as in the previous program, this is the declaration, and you have this initialization of the individual registers, and you have the registers concerned with your interrupt. And getting into this code, VIC interrupt enable register, you will have to make it as 01. So actually what does that signify? VIC interrupt enable register, I am making it as 1. So this enables your watchdog timer interrupt enable. So let me show you the VIC interrupt enable. Yes, this is the interrupt enable register, VIC interrupt enable register. Here you can see the 0th bit is connected with the watchdog timer interrupt. So this particular interrupt I am activating by feeding in a value 01 into VIC interrupt enable register. Then in VIC control 0 register, I am making the 5th bit high and 0. So why it should be 0? Because your slot number of WDT is 0. So VIC vector control 0 register I will show you. So this is your VIC vector control 0 register. Here you can see 0th to 4th bit specifies the slot number, and 5th bit is the slot enable. So when you are making the slot enable, and the slot number we are giving it as 0. Okay, then returning back to the code, I am making this VIC vector address 0 as like equivalent to IRQ handler, that's a label. So where I am writing the interrupt service routine. So interrupt service routine that actually specifies that a particular LED will glow when an watchdog timer overflow happens. Then I am making this IO0 DAR register as 7. 7 represents if I am moving a value 7 into your IO0 DAR register, it means that you are making this second bit, first bit and 0th bit as high. So 4, 5, 6, 7. So I am using port 0.0, 0.1 and 0.2. All the port pins 0.0, 0.1 and 0.2 as output port pins, and I am doing this IO0 clear with the port 0.0 and 0.1, and WD mode register I am making it as 01. So WD mode register, you can see that I am enabling this watchdog interrupt enable set. So I am not making this watchdog reset. So here I am doing this one over here. So only this WD enable I am doing. I am not making the reset to happen. So if in this program, if you are activating this reset also, your reset will take precedence, because reset is the higher priority interrupt. So obviously your watchdog interrupt, so it will not get into the interrupt service routine at all. Before it is getting into interrupt service routine, it will try to reset the microcontroller. You cannot see the interrupt service routine getting executed. So for that reason, I am not activating this WD reset. I am activating only this WDEN, watchdog interrupt enable enable bit. I am setting it high. So that is the value that I am moving into WD mode register, and WDTC I am moving FF. So we have seen the calculation earlier. WDTC is your watchdog timer constant register. So the same value I have specified over here, which will give a time delay of 0.34133 millisecond. Then IO0 set, I am making it as 4, which makes your port 0.2 bit as high. Then I am making this feed right, feed with the AA and 55. Now your watchdog timer will start that is your watchdog WDTV will start decrementing, and your IO0 set, I am making it high. I am moving a value 1, which makes P 0.0 as high, and 0 then after a delay I am making it as I am making the P 0.0 as low. So this I'm again repeating again and again, and as in the previous case I am doing this operation, and so you can reduce these parts as less as you can. So in the initial case I have started working out with different delays for different set of or part of the code, then I have kept it as such. So it can be shortened as for the convenience. So here when the interrupt is happening, it comes into the interrupt service routine, and I have made it in such a way that it goes for clearing your P 0.2 bit and both 0.0 and 0.1 bit also. Then your P 0.1 is set and that is cleared, and then you are clearing the watchdog interrupt flag, and then clearing your VIC vector address, and you are returning back. So this is the procedure that is followed. So let me show you with the simulation. Running the code. So you can see once the feed has been given, your WDTV is starting to decrement. So here, since I have given the delay with 1 AFF, you can see that in the second time when the delay is happening, your interrupt will happen. Here in this case I have used the R8 register. You can see this R8 and WDTV. IO0 set is complete, then it is getting into IO0 clear for port 0.0. Again it's getting into the same delay. Now you can closely observe this R8 and your WDTV. So WDTV is reducing, almost going closer to 0. So now 00 has happened, and it your WD timer overflow has happened. Watchdog timer overflow flag has got set. Now it has come into the interrupt service routine, but the reset has not happened because we haven't activated the watchdog reset. So it will go and make your port 0.2 as high and low. Sorry, 0.1. So normally 0.0 will get activated. Now in this case 0.1 is becoming high and low. So once this part is completed, then it is coming into the next cycle. Again this will get repeated until your watchdog interrupt is happening. So in this case what I have done is I am making this IO0 set as value 4. So this 4 will make your port 0.2 to go high, right? And in the interrupt service routine I am giving this IO0 clear as 4. So this will provide us the time delay between your watchdog timer has started and watchdog timer has got overflow. So that will give us the delay of this one. So to check whether this delay is happening, I have deliberately made this port pin, that is port pin P0.2. So because in the previous code we have used only P0.0 and 0.1. So 0.2 I have used only for checking the time delay. So here you can see that in the main routine, when I am moving a value of FF into your watchdog timer constant register, I am moving 4 into this IO0 set. When you are moving 4 into your IO0 set register, so I am taking this as an example. 4 in the sense your P0.2 will get set, right? So and that will be in high position till your interrupt is happening, right? So interrupt, when does it happen? When watchdog timer overflow is happening, your reset will happen. So your interrupt will happen, and when it generates the interrupt, it goes to the interrupt service routine and it goes for checking the clearing the value of P0.2. So when you calculate the time between that set and this clear, you can understand how much time your watchdog timer is giving us. So for that case, what I am doing is I am just using this logic analyzer and I am connecting port 0.2 over here, and I am just running this code. So you will get a pulse like waveform. So here I can go for checking the time delay between this IO0 set and IO0 clear. So you can see that it is closer to 0.341 millisecond. So almost closer to 0.341 millisecond that you can see in this delta. Delta is 0.342, so that is closer to 0.341 millisecond. So this is the explanation for this code. So as I have already told you, I have created this code a bit lengthier for multiple versions of on and off with the delay. It doesn't mean that these many lines has to be written in as a part of any other code, because as I've already told you, this as in this case I'm using this particular watchdog timer as a part of on off LEDs. So it need not be essentially with the on off LEDs, or it can have an LED for indicating that a watchdog reset is happening or watchdog timer overflow is happening. So for any case, you should understand about how to design this watchdog timer constant register and use it for your convenience. So this is the explanation for the watchdog timer.